Okay, then thanks, Anna, for the invitation. It's really a pleasure to be with you again. So unfortunately, it's not a physical, but a virtual meeting. So it would have been nice to meet also in reality, but maybe that's something we could make up at a later event. Yeah, I'm going to talk a bit about explainable AI for biometric systems, and in particular, making biometric recognition systems robust against attacks. And I will show you some ways how to use explainable AI in order to improve these systems and to make it more difficult for attackers to attack such systems. Yeah, I'm working at Fraunhofer HHI, heading a department there. Fraunhofer is similar to INESC in Porto. It's a research organization. I'm also professor at Humboldt University and host a research group. And we are mainly working on image and video analysis in different kinds of application. And security is one of our application of interest that where we have several activities in analyzing images, videos, faces in order to make, for instance, such e-gates more secure. And in this talk, I will also focus on the problem of verifying a person's identity. And this is something that is relevant for for instance, for automated border control. So if you have been at an airport, which might not be the case in the last time, but everywhere there are popping up these automated border control system where you can identify yourself automatically. So you put on your passport and then the system uses a camera, capture your face and verifies if you're actually the person who you're supposed to be. And this way, the system makes sure that no one can enter a certain restricted area. And this is also something that is interesting for a broad range of different applications. So for instance, for every sovereign task you want to do online, maybe. So if you have a kiosk solution shown here in the middle, you might want to apply for a visa, and also this system has to make sure that you are actually the one you're pretending to be. And this also applies not only to sovereign tasks, but also to commercial things. You have maybe access control to restricted areas. You want to unlock your mobile phone or your computers, you have to verify your identity. And also very recently, there is a lot of activity in verifying a person's identity with some kind of video chat, and for instance, if you want to open a bank account. And for all these problems, you have to verify that you are the right person in order to do to access an area or to do some administrative task. And for that, you can use biometric systems. There are broad ranges of different information that you can use. So in this talk, I will focus a bit more on the face, because that's a very convenient system in order to identify a person. It's contactless, so you don't have to touch anything, which is very advantage for also here in this pandemic time. You can capture from a distance, and it's also very widely accepted as a tool for verifying a person identity, which might not be the case for other biometric features. And face recognition is now a mature technique. It works very well in spite of different challenges like head pose, illumination, aging effects that you have, and that make face recognition a difficult task. So everything seems fine, but there have been many different kinds of attacks recently published or in the last time, and also the technology advances makes it possible to attack such kind of face verification system. They also apply to some extent to other biometric cues like the fingerprint, but here I focus on faces. So for instance, there are face morphing attack where you use multiple images, or in the easiest case, 2 images of 2 different people. You fuse the images, you blend them into intermediate images, and if you can get this image on your passport, then both individuals can actually enter a system which is controlled by face recognition. So that's one threat being published a couple of years ago. Then there's presentation attack, so you don't alter the image on your security document, but you can just alter your own appearance or just hold up an image, a video, a tablet, or anything in front of a camera. And especially if you are in a self-service environment, then this is a threat to these face recognition systems. And very recently, we have seen a lot of deep fakes, which makes it now possible to synthesize new humans or to change the appearance of one human and replace that by another one. And this is, for instance, a threat for these video ident systems where you do a video chat with another person and you can pretend to be someone else, which you are not. And in the following, I will show you some work that we have done in order to detect such threats for these 3 examples. And then later on, I will show you how we can make these detectors more robust using different kinds of explainable AI. So first example is presentation attack. And as I mentioned, this can be easily done by just putting up an image into a camera. And if there's no one looking at you, then the camera has a difficult task in distinguishing a picture of a picture or the picture or the person itself. So since the camera is 2D, then the picture is also 2D. You can also place the image maybe on a t-shirt, which might not be that suspicious, rather than holding up an image. The image can also be animated. For instance, if you have a tablet and then just hold it in front of your face and then show an animation of someone else. You can use 3D techniques. 3D printing is available. You can print a face which you can capture from other pictures using photogrammetry. And yeah, here this is also one example where some guys have hacked the iPhone and opened it using also some kind of a mask. And yeah, this was then possible to fake the recognition system. Yeah, so you can either show something into the sensors or you can just modify your own appearance. Here are just some examples for mask. Here in the middle, you see one example. This is actually one known threat. So this young guy has modified his appearance and pretended to be this old guy, and then he went through a passport control and was later detected. But you can also, instead of wearing entire mask, also use partial mask, change noses, or just using accessories, makeup, or anything else in order to shift your appearance towards another person and to make it more difficult for the face recognition system to detect you. Yeah, so this is a threat to several face recognition systems, and we have been working since a couple of time on finding methods of detecting such attacks on face recognition system. And here we use a multitude of different small detectors which all look at particular details, and then by the fusion of all the individual detectors we can come to a decision whether the person is a correct face or maybe a presentation attack. And we look at cues, for instance, at 3D geometry in order to get rid of flat pictures or display. We look at liveliness detection using information about blood flow and pulse. We use eye blink in order to avoid static prints. And also we look at the dynamic analysis of curvature in the face in order to detect surface manipulation by mask, which have a different surface curvature dynamics. And I will just show you a few or two examples of classifiers that we use, because I refer to them later in my talk. So the first detector that we have built tries to find out whether the person is a picture or a live person. And here we determine blood flow and pulse in the face, and this can be done by a regular RGB camera. And you have, due to the blood that goes through the face, very small variations in brightness and color in the face that you can use in order to determine pulse rate. This is a traditional thing, and you have certainly seen apps where you can measure your own pulse with your mobile camera. But now we extend that system and synchronize to the measured pulse, and then determine for each pixel local blood flow. So we have basically an amplitude of blood flow for each pixel, which is this SNR map. And in addition, we can measure timing to the pulse, a delay. So we have a pulse transition time map, which determines in which in which order or delay the blood actually enters the face. And from these two mask and information, we can now train classifiers to determine whether this is a live human or maybe a picture or a human wearing a mask. And yeah, this works rather well. So here you can see a human without a mask, so you have clear blood flow visible here. This person, or it's the same person, but wearing a partial mask at the nose, so you get some, which can be easily detected because of the missing blood flow or the lower available pulse. And the same thing can be applied here for this chin mask, which covers the chin. So here we have classifiers to determine whether you see skin or something else. And the question is, how good are they? How robust are they? And here we use explainable AI. I come to that later. Of course, maybe if you want to measure blood flow, you also have to measure other activities. So if someone wears a beard or glasses, you cover some areas. So we have another classifier that determines facial attributes, having, for instance, wearing glasses, beard, mustache. And this is a typical deep learning problem, image classification. You put in an image and you get out a class. Here we have classes like gender, glasses, mustache, and beard. And you see they all work very well. High accuracy can be reached with deep learning. So these low values of 97% or 98% are just because for beards it's always difficult to tell whether one wears a beard because there are smooth transitions. Yeah, so we can use such classifier to determine which areas are interesting to analyze. And then we have other classifiers, for instance, looking at the geometry. Here we have different kinds of sensor, high quality sensors or low cost sensors like the RealSense. So we have basically a depth map. We can train deep neural networks working on depth information. And the goal is to distinguish a human face from a flat screen or from a picture of a human. And yeah, so we trained our neural network, and again, we got very good values. So we had 4 false positives for a rather small database, I have to assume, but this is due to the COVID situation. Currently, it's difficult to get test people, but this is these false positive are for each frame. So if you look at the longer frame rate, you can get a very high quality for that. But for all these classifiers, the question is, what have actually the classifiers learned? So the mask, the face attribute, the face geometry. So have we learned the right thing? And yeah, this is also true for another kind of attack. So I mentioned that face morphing attack is another type of attack that we are working on detecting. And the idea is for the attack, you take two images, you align them and create intermediate average views. And for instance, these two images are now averaged average views. So the face area here of these two people are identical. So this is pixel identical. And if you provide, so except for the hair, so we use the hair of just one original image, but the face area is the same here. And if you provide such an image to a face recognition system, those two individuals can actually be accepted by the face recognizer. So we want to find out if someone has modified the image. Therefore, we have also to create different kind of images. You can do that, for instance, by using two images, and it's a typical pipeline for creating face morphs, and there exist multiple tools that you can easily download. So we have implemented our own pipeline for doing that automatically. So you have two images. We search for certain face features that allows you to align the shape or the geometry such that the eyes are on top of the eyes, the mouth are is on top of the other mouth, such that they can fit together. And then we blend and between those images and create an intermediate view. And this works nice for the face image or face area. And as I've said before, the problem is basically the hair, because just blending different hairstyles is difficult. But since hairstyle is rarely exploited by these face recognizers, we just take the hairstyle of one of the original images and blend in the morphed face image. And then we have a morph, and we can use that as a training for our deep neural network that can detect now these morphs. Of course, you can create morphs also in a different way. Here, this is an example where we use a StyleGAN for synthesizing humans. So again, we have two original images. Oh, these are not original, but we optimize the latent vector of a GAN, of a StyleGAN, such that it reproduces a face image of one original, then we create the latent vector of the other person, and then we can blend between those two vectors in order to get an intermediate person. And this is another kind of creation of morphs, which has some other properties. And yeah, here's another example for a female face morph. And yeah, the possibilities of GANs, they increase, so you can even create very high resolution, realistically looking images. So the background here is not correctly, but that would be something that you would have to correct in a post-processing step. These GANs do not only allow to move between two individuals, but you can also move in other dimensions, for instance, moving in the dimension of age, such that you can correct or move the age towards another one. So this is again the original image, and then we have created a younger version of this image and an older version of that image, and that's also possible with these scans. But here in the following, we use only the face morphs, the intermediate blending. And now the question is how to detect them. And we have a large European project called D4Fly, and there we work on different kind of detectors that try to find out whether an image is a genuine image, a real image of a person, or if it's a manipulated version. And for doing so, you can look at different kind of cues in an image. So there are methods, for instance, that look at the low level details, for instance, at the camera sensor noise, at compression artifacts, and other statistical characteristics. You can go a bit higher up and investigate statistics about gradient and blurring and sharpness of the images in order to find out if everything and all locations in the image are in the same statistics. Or you can look at high level artifacts, and that's more what we have been doing in order to find out if the images have been well aligned. So here you see, for instance, some artifacts due to misalignment of the highlights. It can also be semantic properties by mismatching highlights in the eyes, left and right, asymmetries, double eyelashes here, or other kind of artifacts. Yeah, and if you want to detect such kind of artifacts, you can now use genuine images and these morphed images and train a binary classifier, and that's what we have been doing. So we use different kind of deep learning architecture, for instance, VGG19, and then fed that with original views and face morphs, and we could very reliably detect these errors, these face morphs. So we ended up with the equal error rate of 3%, which is a very high risk of an attacker if he get caught with 97%. So it's very difficult for the attacker to pass through that system. The question is, how good is that really? And the last example that I would like to give is deep fake attacks for video ident systems. So usually if you open a bank account, you can do a video chat. So you talk to someone in a call center. At some point, you show up your ID card, and then your identity is verified. But since everything is digital, you can just insert another video stream, put in another camera, capturing yourself, manipulating the video, and send a manipulated video. So for instance, you can manipulate the ID card, so you can track that. We have done that here for another object, and then replace some information on that, or the passport image. But the most problematic attack would be that you can replace your own appearance. And we have now a new project, also a national project, Fake ID, where we work on detecting such kind of deep fakes, but for the particular use case of these video ident systems. And one attack would be to replace the appearance of one person by another one, which is called face retargeting. So you have one person sitting in front of the camera, which is the attacker. Then you have the target identity, and you can use the motion and the expression of the original guy, and then apply it on the target identity, and then synthesize a new video with another person. And deep learning and autoencoders make that possible. And you can animate from different sources, from audio, from video, from feature points, from speech, text, and so on. So this is, their deep neural networks have achieved a very remarkable quality, and you have certainly seen deep fake videos of Obama and many others, Mark Zuckerberg, there was a nice video. And we are also working on creating such kind of deep fakes in order to train our detectors. So what we work on, we don't synthesize the entire frame, but we use some kind of model information. This is some very rough tracking of the face, and then we put on the video on top of that and only replace the video in the facial area. And for that, we also, as many others, we use a variational autoencoder. So we put in the video on the encoder side, create a very low dimensional representation of the appearance and expression of a human person. And then we can use the decoder to synthesize again, the original video. And since we do that both for the texture and also for the geometry in order to have also shape for alignment with the true face. We can train that, and usually 1 minute of video is sufficient to create a nice animation. And yeah, from that we can then we add it again with discriminator in order to get higher resolution results. And now we have a small representation such that we can now animate arbitrary people. So here's just one example here. This is the original video, and this is an animation just from these small latent vectors showing the same video as here. And here we have another completely different animation where we just synthesize something from text. But we can now synthesize arbitrary individuals using text information, feature point information, or video information. And of course, now we have that data, we can train our network, and this is something we are still working on. But similar to the face morph, you can train neural networks and then determine whether this is a fake video or not. But similar to the other approaches, we are not sure what the classifier then actually learned, how he can detect which is a right person, a correct person, or a deep fake. And if the classifier also finds out that something is deep fake, we also want to show why the classifier thinks that this is a deep fake. And this is where explainable AI comes in. And the problem with all these deep neural networks are that they have an astonishing capability in different kind of applications, but they are usually black box systems. So they can do their task very well, but they don't provide you or don't give you insight why they come to a decision. And this might be critical, for instance, in safety or security, critical application like medicine, for instance, where you want to detect a tumor. You don't only want to know that there is a tumor, but also why. And the same holds for critical things like face recognition. It's not only that you want that there's a fake, but you also want maybe an explanation why there's a fake. And also another problem is that you, besides an explanation, you also want to know if the classifier has actually learned the right thing. And this might not be the case. And there is this clever Hans principle. So Hans was a horse more than 100 years ago that was supposed to be good in math. So you could provide mathematical problems to the horse, and the horse could answer them correctly. But of course, the horse couldn't. Oh, pardon? What's the question? So of course the horse couldn't do math, but they found out that the horse learned actually to look at his trainer, and once the trainer saw the right solution, the horse knew that now there will be the right solution displayed. So the horse actually did all the math correctly, although it couldn't solve the problem. And this is somewhat the same problem in deep learning. So you can train a neural network such that it answers for your training set the right or gives the right answers, but need not be general for new solutions. Yeah, and this is especially important since neural networks might be very sensitive towards small variations in the input. You all know of these adversarial attacks. So for instance, if you have here an image and a classifier saying this is a stop sign, you can add a small, very small noise. It need to be commuted in a certain way. You can put that on top, and although these images look almost the same, the classifier just tells something completely different. So network might do things that they shouldn't do, and so we have to make sure that yeah, we can get some insight or explanation why the network came to this decision. And there are different tools of doing that. So very old version or simple version is you just hide some parts in the image and look if the classifier still comes to the same idea. So if you want to classify this image and see if there's a castle in there, you can just mask some areas, and if you mask the castle, then maybe the classifier says, no, there is no castle anymore. And then you know that there might be a castle under this. And with that, you can also create some kind of heat maps, but it's very slow and maybe not the best way of dealing with that. There are other tools that look at different gradient information and do a Taylor decomposition of the network. So for sensitivity analysis, you can look at which areas basically influence the decision of the classifier, and what kind of pixels do I have to modify in order to get the most deviation in the classifier outcome. This also works, but since you have a lot of gradients, and usually for very deep networks, this can lead to noisy versions. So there are other extensions by smoothing gradients or integrating over gradients in order to make that more robust. Yeah, I show here another solution, and this solution is yeah, one tool that had been developed by our colleagues at HHI. It's layer-wise relevance propagation, and there the idea is to do a forward pass and a backward pass in a neural network. In the forward pass, you put in your image, then you compute all the activations, you come to a certain classifier decision, and starting from this classifier decision, you propagate the relevance through this network layer by layer. So you start from the last neuron, and based on the weights that you have here, you determine which neuron of the previous layer were relevant for this decision. And then once you have that layer, you move to the next layer, and you can propagate that to the previous layer. And at the end, you have some kind of a heat map showing the relevance of the individual areas in the image. And this propagation can be done in different ways. So they provided different rules. For instance, you can do that according to the weights. This is similar to the sensitivity analysis. But this leads to some kind of noisy input. You can reduce noise and produce sparse results by adding a small epsilon in the normalization of the weights, meaning that if all weights have, or if all activations are low, then basically the relevance is put in direction to 0. So this leads to sparse solution. Or another rule could be to emphasize a bit more on the positive activations, positive weights. So here you have the regular weights, and then with the additional parameter gamma, you add only the positive weights, so shifting everything to positive activation. And you can see how the outcome of the heat map looks for this example and the class castle. Now you can combine, and this is some kind of recommendation they found out. So start for the lower layers with these weight-based or just LRP 0 rule, and then for the intermediate layer you try to sparsify the heat maps, and then having the gamma law here for the higher resolution. And if you do that, you get a heat map that clearly shows what kind of pixels actually led to a positive activation of the castle, here shown in red, or maybe in blue, which inhibits the detector to tell that there is a castle. Yeah, and compared to sensitivity analysis, for this examples where you want to classify cars, you can get clear or at least better outline of these regions. And you can now use these examples in order to prove if a classifier works or has learned maybe wrong things. And here, these are examples for classifiers that were proposed in the Pascal-Vogt challenge, where they actually provided the right solution and classified the image correctly, but based on a wrong assumption. So here, this is an example for an image of the class horse, but when applying LRP, they found out that actually the classifier does not look at the horse for classifying horse images, but on the copyright tag. And this was due to the fact that in the training database, there were a lot of horse images having a copyright tag. So the classifier was clever and learned if there's a copyright tag, then it's a horse. But of course, this is not what you want. And the same here. Here, the classifier learned if there's water, then there's a ship, which might not be true. So this is something you can get with LRP or other kind of tools. Another nice example what you can do with these explainable tools is here an experiment that we did in the classification of here images showing magnetic surfaces, and there were some defects, some cracks in there that need to be detected, but the images were just labeled okay, or this image contains a crack. So there was not a segmentation or something like that. So it might be simple, but you see here, these are images without a crack. So there are also some other artifacts which need to be distinguished from crack. And although only the images were labeled, you can now run LRP, and LRP tells you which pixels actually contributed to the decision that this image contains a crack. And what you see is that you actually highlight the crack. So if you do some kind of thresholding, you can then basically segment the crack. And this is also one way of creating, for instance, labels for data sets where some kind of labels are missing. So here you just had labels for the entire image, but you can get pixel labels using LRP. Of course, this might not work perfectly, so you might have to correct these labels. Yeah, but now coming back to our original problem with all these classifiers for presentation attack, face morphing attack, and so on. And I showed you this very simple classifier classifying gender, glasses, mustache, and beard. So that worked very well. So we run LRP to verify that. And yeah, this works quite well. So we see here for glasses, LRP highlights the frame of the glass, which makes sense. So the classifier looks at the frame. For the beard, actually it looks at the region around the mouth, and for the mustache and for this entire beard, it looks also at these regions. So here in this case, we were very satisfied with the results. So the classifier that we learned or trained learned actually the same or the right thing based on these LRP results. The other example, presentation attack, where we looked at the depth map, which also very good results, but running LRP, we found out, oh, the classifier does not look at the geometry of the face, it basically looks at the outline, so at the depth discontinuity. So if there's a person, so we have something, the person and the background, and in between there's a jump, and the classifier only looks at the outline. And if you put on a tablet in front of your face, then the outline of the face changes, and this has been learned by the classifier. So that might not be what you want. So we found that out because now you could think of maybe printing a face image and then cut that out with the scissor, and then it would work again. So the classifier would fail. So we modified our classifier. So we did some kind of face detection, and then we cut out the face region so we get independent of the silhouette. And here, yeah, for a correct face with a good sensor, then LRP tells us, yes, it's a face. Blue is against the face. Even for this low quality geometry of the Intel RealSense, we get a recent result. Most of the errors are actually saying, yes, it's a face. If someone puts some fingers in the face, you see the unoccluded areas are still saying, yes, it's a face, but the fingers are here marked in blue, so it's recognized. A bent image where you use a picture and then simulate some geometry, you see some regions might yeah, be close to a face, but others are not. And for a display, you get complete mismatch. And yeah, this is a nice example where explanation has actually led to a better classifier. And yeah, we can do similar things for face morphing detection. Yeah, as said, we had a very good result with our initial simple classifier, 3% equal error rate. But looking at LRP, we found out, oh, the classifier basically looks only into the eyes of the image. And this makes sense because the eyes have high frequency. So if there are artifacts, they're most easily be detected in the eyes. But if you know that, you could then create a face morph where you morph everything in the face except for the eyes, and the classifier would fail. So we found out, and then we did a similar strategy. So we created partial face morphs where we just replaced here the black area. So it was not black, but the black area was replaced by the face morph. So we just created a morph of the left eye, the right eye, the nose, and the mouth. And we trained a multi-class network that actually can determine which area is morphed and which is genuine. And thus we enforced the classifier to look at all different regions in the face. And then we removed the last layer of the network and retrained it for the binary classification, and that worked much more robust. And if you look now at the LRP results, so the classifier looks at different areas into the face. And yeah, and such a classifier is also more robust to other attacks. So this is shown here. So in the beginning, we had an equal error rate of around 3%. And for our multi-class enhanced version, we have basically the same equal error rate. But if we provide only partial morphs to the system, the naive approach basically breaks. And yeah, you could argue, yeah, of course, it has never seen such kind of partial morphs, so this is true. And the multi-class actually performs much better. But he has also seen these partial morphs. So this is not very astonishing. But if you now apply a completely different attack, which is here some adversarial attack, adding some kind of noise, which has nothing to do with these partial morphs, we found out, yeah, that the robustness is much higher. So if we apply this attack to the naively trained network, it basically breaks down. But this multi-class network, yeah, has a high recognition rate. And yeah, so we can enhance the amount of noise, and you see the more noise we add, the lower the accuracy get. But for a certain noise, and here in this area we have something, it starts being visible. We have a large gap between these naively trained systems and the enhanced trained that we experience through the explainable systems. And that motivated us of extending this approach, creating more variation of our input database. So we exploited also neural style transfer methods in order to enhance the morphs. And neural style transfer is a technique that you have certainly seen before. It's this nice method where you provide two images, one original image having the content, one other image presenting the style of an image, and you can then apply the style to the original image and then create a new image showing the content of the original image in the style of this style image. And of course, you can do similar things with faces. Get an original image of a face and some painting of a face, and then create something that looks like a painting of this original face. But that's not what we want to do, but we want to do the opposite thing. We want to create something from a face morph that has been computed from two original images, and this face morph might contain some artifacts. The original images do not contain artifacts, so we apply neural style transfer techniques onto the face morph in order to create an enhanced morph that has the content of the face morph, that looks like the face morph, but with the style of an original image. So here we have to provide two styles because we have two images in contrast to the original version. But then we say, oh, we want to have an artifact-free. The style is artifact-free, and we can remove some artifacts in the enhanced morph. And here you see magnifications. Here you see, some blurring and some kind of artifacts. And this gets much better if you apply this neural style transfer. And this also works for the entire face morph. So here it might not be visible if you look a bit in. I'm not sure if you see that through Zoom, but here you see all the skin pores and the eyes are much clearer and sharper compared to the original computed face morph by applying these style transfer techniques. Yeah, and then we tried to see or to measure the influence of such enhanced face morph attacks on different kind of face morphing detectors. So we investigated here three different detectors from the literature, some kind of edge feature-based detector using SIFT and other features, a local binary pattern, statistical image features, and then our two DNN-based classifiers, the naive one and the multi-class one, and we compared their influence on on images that have been computed with the additional face morph enhancing techniques by the neural style transfer. So so we have different kinds of attacks. We have the simple morphs. These are just the usual face morphs. Then we have the enhanced, the improved morphs using neural style transfer, but we also tried other possibilities to enhance a morph by using some kind of histogram equalization or sharpening filters, which also enhance the quality of a blurred image. And now we measured the quality of these detectors. So this is measured at BPCER and APCER. So, and this one is the attack presentation classification error rate, and the other one is the bona fide classification error rate. And here the numbers basically gives you the percentage of morphs that are not detected by the classifier. And if we train the classifiers with simple morphs and then test them also on similar morphs, then we get some certain values, and all these detectors work quite well. If we just use enhanced morphs, and yeah, the detectors have never seen these enhanced morphs, then basically all detectors break down. So they have a significant drop in recognition quality. Yeah, and this is also the case if we use other yeah, enhancement techniques. So also sharpening or histogram equalization for all these. So one detector performs better than the others, but in principle, all of them degrade. And even if you combine techniques, so enhanced morphs plus histogram equalization, you basically add the error. So it gets worse and worse. So then we used also this enhanced morph, similar to our previous cases, for training. And yeah, so we had a new training database that had 50% of these traditional morphs and 50% of enhanced morphs. And if we then show the simple morphs, basically we get the same results. Nothing has changed. But if we show these enhanced morphs, now the detectors perform much better than previously. And of course, this is not astonishing because they have also been used for training. But yeah, these detectors also perform much better for the other techniques. So by just spreading the range of possible yeah, attacks in the training database, you get also more robust to other attacks, to unseen attacks that have not been seen before. And that's a nice thing, because this makes it easier. You have to add variation in your training database, and you get more and more reliably or more robust towards new attacks that might occur. Yeah, and a last thing that I would like to mention here is the use of these explainability techniques like LRP to support humans in order to show the outcome of a network decision to a user. And we have seen that you can use, for instance, LRP or another tool in order to find out if the classifier has learned the right thing. You can optimize your classifier and creating it more robust. But yeah, it might be something for a technical expert in order to evaluate these heat maps and these results. But it would also be nice if you can provide such kind of images to a non-technical expert, for instance, a border guard or enrollment officer. And for instance, if maybe some face verification is not correct, such that the recognizer say, oh, look at the nose. I think this nose does not match. Or if you have face morphing detection, that the system does not only tell you, oh, there is a face morph, but look at the right eye. This might be suspicious, and please have a closer look. And you can use these techniques for that, but yeah, there might also be some problems, because these deep neural networks are very complex functions, and you have a classifier that has a very sophisticated structure, which makes it sometimes difficult to interpret the results. And this is shown here. Here we have again our partial face morphs, and we have just morphed the left eye of this guy, and everything else was genuine. And running our simple naive classifier, and these are average results, shows that that the detector clearly detects also this modification. But running our multi-class detector, which was trained a bit more sophisticated, ended up that for some people, actually the wrong eye was highlighted. So although we modified the left eye, LRP showed, oh, there's yeah, some activity in the right eye. And yeah, this is due to the fact that LRP shows what kind of region has a lot of activity or activation that led to a certain decision. And we found out that this classifier has actually learned to compare left and right eye. And due to this clipping of positive activation and negative activation, it can end up that actually the good eye is highlighted, although it's compared with the wrong one, but it's just incorrect highlighting. And this might be difficult for someone to interpret if his or her is not a technical expert. So we came up with a modification of LRP, which we called focused layer-wise relevance propagation. And it's very similar to LRP. So we have a forward pass through the network once we have applied an image. And LRP then starts from the last neuron and propagates the information back. And for FLRP, we just look at the first layers, the convolutional layers, which don't have the fully connected classifier information. We just propagate that information back to the frontmost part. And because these feature maps here are still localized, we get a very nice localization of the activation in the original image. Of course, we somehow need to find a certain activation from this layer because we don't use the back propagation from the last fully connected layers. And we do that by looking into the deep feature maps for those neurons which has the most variation between morphs and genuine images, and these images are initialized and then back propagated to the original version. And if we compare that with LRP, we get very similar results. So this is a face morph, and both LRP and FLRP show similar results. They highlight the areas where the classifier thinks there might be some artifacts. But especially in the cases where the classifier is a bit unsure, or even if the classifier is incorrect, this FLRP can highlight still the suspicious region, even if they are not enough for the classifier to decide that this is a face morph. So this is again a face morph. The classifier had said, no, it's not a morph, but I'm not really sure. And if you look at LRP, because there was the incorrect decision, this does not show really the artifacts in the image, but with FLRP, we can now clearly see the artifacts still in the image, because this image here shows some clear blurring effects, while this eye here has a better blending quality. And also here there are some artifacts visually visible, and they are detected by FLRP. And also our original problem with the flipped eyes is circumvented by FLRP, because we are just looking at the convolutional layers. And here in this case, it's not a partial morph, but here this eye here is very badly aligned. So this has clear artifacts, which is highlighted here, and LRP has flipped here these eyes and show something in the other eye. And if you're more interested in this particular tool for visualizing classifier decisions, there will be a presentation later this day in this workshop. So you're happy to be to join the talk there. Yeah, and with that, I would like also now to conclude my talk. I've shown you different kind of attacks on biometric systems, and also shown you that deep neural networks can really help in detecting these classifiers. And the main problems to make them robust against future attacks. And so we have also seen that broadening our database and putting in some variation in there is a very good strategy in order to be robust against unseen attacks. And yeah, in order to increase robustness, yeah, you can use explainable AI like LRP in order to find out if your classifier has learned the right thing. But you can also use LRP or FLRP in order to highlight to someone where actually a problem lies. And this can help in order to make a biometric system more robust if you have an automatic system, but also some humans that can check, which is, for instance, possible at an airport control. And yeah, all these tools are just very simple tools for classifiers, so it would be nice to extend them for other kinds of input, for instance, like video. And I'm very looking forward for new solutions there for enhancing explainability in AI. With that, I would like to conclude my talk. Thank you very much for your attention. And I also want to thank here my people in my group that have contributed to all these works that I've shown here. Thanks a lot. And yeah, if there are questions, I'm happy to answer them.